All right, guys, it's time for some fun with math. And so today we're going to continue on with our different types of integral tests. So last time I think we saw the divergence test. So this time we're going to talk about something called the integral test, and then we'll talk about these p-series again. So I mentioned these in a few videos ago. But today we'll define them and talk about when they converge and diverge. So first, let's just take a look at this integral test here. So the integral test, of course, it's a test that uses the integral. And so what does it say? If you have this infinite series S here, and you define this function f of n to equal a sub n, so just the terms of your series, and if it satisfies these two conditions, the terms must be positive and decreasing, which means they're getting smaller as n gets bigger, then the following holds. So first, if you look at the improper integral here and it converges, then we get to automatically conclude that S converges. Or if you look at the improper integral and it diverges, then we automatically get to conclude that S diverges. So this is a nice little test. Of course, you can't use it on every single series. A series has to have positive terms, and the terms have to be decreasing. As to why it works, we'll find out in a little bit. But first, let's just do some examples so I can show you how you use this test. All right, so how to use it. So we're going to use the integral test to determine if each series converges or diverges. So let's take a look at our first series here. So this is the sum n equals 1 to infinity of 1 over n. And we're going to make our function f of x equal to 1 over x. And then notice, so f of x equal to 1 over x is decreasing and positive. So let's start with the positive first part. So it's positive and decreasing, and you're going to love how we show this, so positive and decreasing, because, and all you have to do is just graph this on your graphing calculator. So here, I always say, let you get away with murder. So we're going to go from 1 to infinity, and on your graphing calculator, you're just going to graph 1 over x, and we're going to use that to show that it is positive and decreasing. So 1 over x, we'll make our window, let's just make it go from 1 to 10, and then we'll just zoom fit it. So 0 zoom fit, and there it is. And so basically it starts up. So let's come up here. So it starts up here and then just goes down. In fact, when you plug in 1, you get out 1. And that's how you show that something is positive and decreasing in this type of problem. Now that's just the criteria. So now we know it's positive and decreasing. And now we have to show whether the improper integral converges or diverges. So we write the integral from 1 to infinity of 1 over x dx. And I'm going to let you get away with some murder again. We're not going to use the limit on it. We're going to treat infinity like a number because I've already tested you on improper integrals. And as long as we're very careful with that infinity, we're going to be okay. And so then what can we say here? So this improper integral, and you can give it a name if you want. So sometimes I call it I. I don't know if I'm going to use that or not. This is just equal to ln of absolute value of x from 1 to infinity, which equals ln of infinity. You can drop off the absolute value because infinity is quote, quote, positive, and then minus ln of 1. And so that's going to be equal to infinity minus 0, which just equals infinity. Therefore, what can we conclude? So that improper integral diverges. So that means that our series, we'll call it S. So therefore, S also diverges. So it diverges. And this is then by the integral test. It's a nice and easy little problem. And what's nice about the integral test, it's not just a test that can give you divergence, but it could also give you convergence. So let's do another problem here. me get this back in shape, guys. Sorry. Just go down. Let's look at this next series. We'll call this one S. And what do we want to do? So we define a function f of x to be equal to, so you just take the terms of the series right here. So we have 1 over x times that ln of x quantity squared. We want to say that this is positive and decreasing. So is positive and decreasing because I'm missing my words here. So decreasing because why? Because, and you just have to graph it. So that's all you have to do. So take out that graphing calculator and we're just going to graph this. Now, when we graph this one, we're going to graph it from 2. I think up to 10 probably should be good. So let's take a look. So over here, I hit y equals. I clear this out. I do 1 divided by. Now this one, since you have x times ln of x quantity squared in the bottom, you have to put parentheses around the whole thing. So left parenthesis x, left parenthesis ln of x, in parenthesis for the ln function, in parenthesis so you can square the ln function, and then in parenthesis for the denominator. We'll make our window now go. Notice the index starts at 2. So we'll start it at 2. If you start it at 1, it blows up there. So you want to start it where it starts, so 2. And then zoom fit it. So zoom, you hit 0. We're going to zoom fit. It'll fit the output to the input. And this will give us conclusive evidence that it's decreasing in positive, clearly. All right, so when you plug in 2 here, you get out some sort of point right here. If you want, you don't have to label it, but I can know what it is. It's 2 ln of 2 quantity squared. So you have that height, and then it just starts up and then starts going down, basically, and heads out towards height 0. All right, let's fix that a little bit. There we go. It's hard to draw in here, guys. So try to draw better than I'm drawing. I'm on a tablet right now. Sometimes I get to draw. I have a nice screen, but now I have a tablet right now that I'm drawing on. Okay, what's next? So it's positive and it's decreasing. And so now we're going to look at that improper integral. So we're going to look at I and see what happens when we integrate from 2 to infinity. So why do we choose 2? So very important we pay attention to this index here. So we're going to start it at 2. And then we have 1 over x, parenthesis, ln of x, quantity squared, dx. And again, we're going to get away with murder here because I'm not going to make you write the limit. We're going to treat infinity like a number, and as long as we're careful, we're going to be okay. And so now how are we going to integrate this? So this one, it's not one of our types like the last one. And so we're going to have to use one of our techniques of integration. And if you try to figure out which technique to use, you should always look for substitution first. And so what we're looking for is a function, and then it's the derivative, and there it is. And so we're going to let u be equal to ln of x, and then du will be equal to 1 over x dx. And we'll change our limits of integration. So notice you have u of infinity is equal to ln of infinity. And again, we're not going to do any math. I know ln of infinity is infinity, but we're going to wait to the very end to do the math, basically. And then u of 2 is equal to, and we're just plugging into the u function there, ln of 2. And so this will be equal to the integral from ln of 2 to ln of infinity. And then we have 1 over, and then this is our u right here, so that's going to be u squared. And then this 1 over x dx, that's this stuff right here. And so that's just going to be my du. And so this is going to be equal to the integral of ln of 2. So this is one of my types. So I'll write this as u to the negative 2 du. And I can integrate that by simply adding 1 and dividing by it. So u to the negative 1 divided by negative 1. So you add 1 to the exponent and divide by it. And I'm going from ln of 2 to ln of infinity. And so that's equal to negative 1 over u from ln of 2 to infinity. which equals, and now I'll plug in my infinity, ln of infinity, right? So let me fix that. So that should be ln of infinity. So right here, evaluated from, and I have ln of infinity. So -1 over ln of infinity. And then minus, and then a negative makes this a plus, and then 1 over ln of 2. And so that's going to be equal to, now ln of infinity is like infinity, so 1 over that is going to be like 0. And so I just get 1 over ln of 2, which is an actual number. I don't know what number that is, but I don't even care about the actual number. I just care that you get something out, that it converges. So then I can conclude what? So here, we'll write therefore, our series S converges, and then don't forget to write y, by the integral test. All right, so let me zoom out here so you can kind of get a better picture of what's kind of happening. And so here are the two problems we just did, right there. And we're using what's called the integral test. And so when you use the integral test, you just don't forget, I'm going to let you get away with murder here. You just have to make the function, say it's positive and decreasing, and give me a reason why. And the reason why, you just take the graph, right? There are other ways to show things that are, decreasing, like you could take a derivative of this thing and show it's always negative. That's one way to show it's decreasing. You can also show it's decreasing by setting up an inequality, which we'll talk about later. But in this problem, it's like just use the graph, right? So in each of these, you make the function, you say what it is, and you back it up with a little graph using your graphing calculator. And then the hard work is usually done in the improper integral. And notice, in this improper integral down here, you got at a number. Now that number is not the sum. So be very careful. S does not converge to 1 over ln of 2. I don't know what S converges to. I just know it converges. So this test just is a test for convergence in the sense that it converges, not what it converges to. All right, so that's important to note. All right, so let's move on. And so I want to talk about why this works. So I just want to give you kind of a sketch as to why this actually works the way that it does. So if we assume this improper integral actually converges, what does that tell us about this sum? Well, check out the picture over here. So here's my function, f of x. So my f of x, remember, this f of x is just going to be equal to, or in this case, f of n is just equal to your a sub n's. That's how we define the function, basically. And what you want to realize is that the a sub n's can be represented as area. And so what's a sub 1? Well, right here, if you plug in 1, you get f of 1, which equals a sub 1. So this height right here is height a sub 1. And if you go back, you get a little rectangle. So a sub 1 is just the area of that rectangle. And then guess what? What's a sub 2? Well, it's this height right here. So that's a sub 2. And so if you go back, this area right here can be represented by the number a sub 2, and so on and so forth. So you just keep on going. So here is height a sub 3, and then you multiply by 1, and you get that area. So that's a sub 3, and we'll do one more just for fun. And so right here, it's a sub 4. And so that's that area right there. Let's do that in. So a sub 4, where the height above 4 is a sub 4. And so just hit dot, 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 because what you're doing is you add up all these little areas, and notice they all fall below the area underneath the function f, which is represented by this integral. So what does that mean? That means when you add up all these a sub i's, or a sub n's if you want, so a sub 1 plus a sub 2 plus a sub 3 plus dot, 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 they always fall below that improper integral. And so if that improper integral converges, which means what? Which means this thing is equal to some sort of number, I don't know what the number is, but some positive number, that's going to force this to be some number. Again, I don't know what that number is, but it's some number. So because this series is less than or equal to that improper integral, and we know that improper integral is equal to some number, it implies that S converges too. And so that's why the integral test works. When the improper integral converges, it forces the series to converge. And going the other way, the same thing sort of happens. So down here, we'll assume now that the improper integral diverges. And we want to conclude then our series has to diverge. And so why is that the case? Well, notice here's height a sub 1 again. And now this time, instead of going to the left, we're going to go to the right. So the rectangle lies above it. And so that area, again, is just a sub 1 times 1, which is a sub 1. And then we'll do the same thing for when we plug in 2, you get out height a sub 2, and you make the little rectangle going to the right now. And notice that rectangle lies above the function. That's why it's important for the function to be positive and decreasing. Right? As it decreasing, it forces that little rectangle area, that rectangle to be above it. And then we do it again. Here's a sub 3, and we make our little rectangle. And so the area for that one is just a sub 3. I guess I should have written this a sub 2, and so on and so on. And so what happens is if you add up all these little green rectangles, they lie above the improper integral. So the improper integral here starts at 1. And so then notice it lies below, right? The red area lies below the green area, basically. So if the red area is infinite, it diverges basically in this case. And it's infinite because everything is positive. So there's only one way for it to diverge is if it's all positive and decreasing. I mean, that's important, positive and decreasing. It can only basically diverge to infinity. So what's happening here is we're saying basically I is less than or equal to the series now. And this I is going to diverge. It's going to go to infinity. So that's going to imply that that green area is also going to be infinity. So S will also diverge, or S diverges also. So it's a nice little area argument. And I just realized I made a little mistake here. I guess up here for that a sub 1, my integral is actually starting at 1. So I should probably take off that red area right there because it's not really being counted, right? That piece right there. But that's okay. That's just one term. So basically what you're saying is, all these green areas after a sub 1, they're going to converge to a number because it's below the red area. And then you could just add on some number at the end. It's going to still converge. But that's the idea. It's just an argument. So it's just like this guy. So it's like, hey, if the area underneath this guy is finite, the area underneath that guy is finite. If the area underneath this guy is infinite, the area of the one above it is also infinite, right? So it's just that simple idea. And that's why the integral test works the way that it does. All right, let's move on. We got a few more things I want to cover with you guys. So I guess one last thing really, which is p-series. And so basically there's 3 types of series and really just 2 that are really important. So geometric series and telescoping series we found. Telescoping is really a novelty, so it's not really that big of a deal. But geometric are super important. And then the other one that's really important are p-series. So these are important because we're going to do something called the comparison test in the near future here. And to do a comparison test, you have to have something to compare your series to. And so the idea is we can use either p-series or geometric series to compare other series to, and then conclude whether they converge or diverge. So what the heck is a p-series? So you're going to let p be any real number. That means it can be positive, negative, 0. It could be square root of 2. It could be 2. It could be any real number you want. And then the series here is called a p-series. And so let's just write out a few of these terms. So, here we start with n equal to 1, just so you can kind of see what happens. So when you plug in 1, you get 1 over 1 to the p, which is really just 1, and then plus, and then we let n be equal to 2, and you get 1 over 2 to the p, and then n equal to 3, so I don't think I need to write n anymore, so 3 to the p, and then you can kind of see, oh, there's a nice pattern here. So 1 over 4 to the p, plus dot, dot, dot. So that's what a p-series basically looks like. And we actually know when it converges and diverges. So p-series converge if p is bigger than 1. And then they diverge if p is less than or equal to 1, which is kind of, some of it's kind of obvious. Like notice when p is less than 0, so suppose p was equal to negative 2, if you have 1 over n to the negative 2, remember that's really n squared. So if you sum up 1 over n to the negative 2, if you sum up n squareds, of course it's going to be infinity, no matter where your index starts. So we'll start at 1 to infinity. But it's always going to add to infinity. So sometimes it's pretty obvious, but other times it's a little tricky. You know, what happens when p equals 1? When p equals 1, we get this sum of n equals 1 to infinity of 1 over n, which we saw with the integral test. It actually diverges, but it's not clear that this thing is going to diverge just by looking at it, because if you take n squared, p squared, or p equal to 2, you know, you get 1 over n squared. It turns out that that converges. This one actually has a name. It's that important. It's called the harmonic series. So I don't think I've pointed that. I haven't said that to you guys yet, but I will start talking about it later in some later videos. We start talking about what's called conditional convergence. So this one actually has a name. It's called the harmonic series. But let's focus on p-series. So let me just give you some examples of working with p-series. And so how p-series work. And so we want to determine if the p-series converges or diverge. All right, so let's just take a look. This one's nice and easy. So p is really clearly equal to 2, right? Because remember, a p-series looks like this, the sum of 1 over n to the p. And p is actually bigger than 1. So therefore, this series S, so S is a p-series. Oh, therefore, this is right. Therefore, S converges because it is a p-series with p equal to 2, which is bigger than 1. I think that's good. All right, so it's a p-series with p bigger than 2, with p equal to 2, which is bigger than 1. And so to conclude convergence on this one, we have to say, you know, it's a p-series, what its p-value is, and if it's bigger than 1 or less than or equal to 1. Let's look at this one here. And so this is the sum, n equals 1 to infinity, and I'm going to write it as this n to the p, right? So it's 1 over n to the, and then the square root, remember that's to the 1/2. And so notice my p is equal to 1/2, and that's actually less than or equal to 1. So therefore, my series S, it doesn't converge, it diverges. So S diverges because, again, it is a p-series. So we identify the type of series with, and we have to say the p-value, with p equal to 1/2, and it's less than or equal to 1. So when p is less than or equal to 1, you get divergence. When p is bigger than 1, you're going to get convergence on these p-series. And we haven't said y yet, right? So the y is still to come. So we'll hit the y here in a minute. And then finally, this one here, this one's kind of tricky. So we want to write n, so over here, we want to write n as 1 over n to a power. So that's not that easy to do. So you have to work on that. Think about that for a minute. And so this will be equal to the sum, n equals 1 to infinity. Let's use red here. So it's my series S. And that's 1 over n to what power? And hopefully like, oh, it's just -1. If you put -1 there, it shoots it back up into the numerator, and you just get back n. And so now p is equal to -1, which of course is less than or equal to 1. So therefore, S diverges because why? Again, it is a p-series with p equal to -1, which is less than or equal to 1. And so that's how we use p-series to conclude convergence or divergence. But it only works for p-series, right? So it's a very particular type. It's kind of like for geometric series, you look at that R and make sure the R lives between -1 and 1. And that's where it gets kind of confusing, right? So you have to kind of, separate things, understand, a geometric series looks like this, a p-series looks like that. Geometric series converge when that absolute value of R is less than 1. P-series converge was when that P is bigger than 1. But it'll take a little time to kind of get that straight. Now, we have a little time left, so let's just take a look at why this is the case. So why it actually works. So, why when P is bigger than 1 do we get convergence? And why when P is less than or equal to 1 we get divergence for our P-series. And so let me just kind of come down here and we'll talk, and this will take some thought on your part. I just kind of sketched the proof of this. And so, we're going to let P be any real number, and then we'll let our series be that P series there. And at first, we'll assume that P is less than or equal to 0. And if P is less than or equal to 0, guys, that basically means it's negative or 0. If you look at this limit, guess what happens as n goes to infinity? So just if you want to look at one case, like P is equal to 0, if you have 1 over n to the 0, that's just equal to 1 over 1, because anything to the 0 power is 1, so that's 1. So if you look at the limit as n goes to infinity of 1, you get back 1, which is not equal to 0. And so if it's not, the terms don't go to 0, we know by the divergence test it's going to diverge. And then if P is less than 0, which means it's negative, so you have 1 over n to the P, but P is negative. And so what happens when you let the limit as n goes to infinity, this will be equal to 1 over infinity to the P, but again, P is negative, P is less than 0. So when P is negative, it shoots it back up into the numerator up here, and you get infinity to the negative P, and now negative P is positive, that's bigger than 0, so it's going to equal infinity. So basically, when you have this condition, P is negative or 0, then the limits of those terms are not going to go to 0. And so since they're not equal to 0 here, we can conclude, therefore, S diverges by the divergence test. And so right away, you get everything for P less than or equal to 0. Now, we're looking for divergence on P less than or equal to 1, but we've got a lot of it, right? So we got less than or equal to 0. Now we just have to look at P being between 0 and 1, or equal to 1. And so now let's look at the next case. So now let's assume P is positive, and we'll define our function f of n equals 1 over n to the P. And guess what I'm going to do? I'm going to do an integral test to show when this converges or diverges, because if P is bigger than 0, then f of n will be positive and decreasing. And that's because, again, my p-value here, move this over, my p-value is positive. So basically, that denominator is going to get bigger and bigger each turn as n gets bigger, which causes the whole thing to decrease because it's 1 over. And so now we're going to look at this improper integral. And so for this improper integral, I plug in my function there, 1 over x to the p, and then I have some cases. So notice when p equals 1, you have the integral of 1 over x basically dx. And so that's going to be ln of absolute value of x. And then when p is not equal to 1, we'll split up into these two separate cases. So when 0 is less than p is less than 1, you just add 1 to the exponent and divide by it. When p is bigger than 1, again, you just add 1 to the exponent and divide by it. Right? That's the rule. Right? So you have these sort of three things happening, and then we just plug in our limits of integration. So down here, I plug in my limits of integration. So, I'm just plugging in my infinity and taking off when I plug in 1. So I plugged in infinity and took off when I plug in 1. Plugged in infinity and take off when I plug in 1. Plug in infinity and take off when you plug in 1. And so now I need to interpret what I get here. And this is kind of the tricky part, if you want, is you have to kind of think a little bit about what's happening. So some of these are easy, like this one's super easy, guys. So that's going to be infinity, and that's going to be 0. So this is basically going to equal infinity. So it's definitely going to diverge when it's equal to 1. And then up here, think about what minus p plus 1 is. So p is a number between 0 and 1. So it's like a half or a fifth or 7/8. It's a number between 0 and 1. So if you have negative that number and you add 1, it's that exponent is always going to be positive. And so infinity to a positive exponent, well, what's going to happen there? This is just going to give you infinity. And so you can get infinity minus some number, which is going to just be infinity. So when you're between 0 and 1, oh, I guess here I should actually write 0 is less than p is less than 1, right? Because we actually took care of all the negative already. So that was a typo on my part. So when you're between 0 and 1 or equal to 1, you're going to get infinity because you get infinity in both of these cases. Versus down here, when p is bigger than 1, think about what this exponent is. So when p is bigger than 1, you take negative that p. So that means negative that p, it's like negative 1 or to the left of it. And so if you add 1, this is always going to be negative. And so you have infinity to a negative number. So what's going to happen to this one? This is just going to be 0, right? Because it basically have infinity to a negative number. And so that's just going to give you 0 there. And then over here, you have minus, and then here you have another minus. So you actually write this as 1 over what? P minus 1. So that's actually going to be that limit. So this is actually going to be a number. So some 0 minus some number, and I put that minus on the inside, so I get positive p minus 1. And so what can we say then? So therefore, putting all this together, so let me zoom out a little bit. So putting all this together, what can we say? We can say for p, less than or equal to 0, or p between 0 and 1 or equal to 1, so that's basically p less than or equal to 1 right there, we know that the p series diverges. And then for p greater than 1, we just showed you get out some number, and so the p series is going to converge when it's bigger than 1. And that's the idea, right? So that's why it works the way that it does. And so you need those two tests to show this. You need the divergence test and you need the integral test. And why are these tests nice? It helps us avoid the definition, right? So that definition is super hard to use in general. So what we do is we create these nice little tests that we can apply in certain situations. Not every series can we apply this to. You know, some series just don't have a test that works on them. But the ones that we see, we can apply one of these tests. All right, that's all I have for you guys today.